Welcome back. We continue with inverse variation. Now we look at example 2, the second example. So given that Q, now look at the way it is written, the word inverse variation doesn't appear. So the question requires you to interpret this language. And this means that Q is inversely proportional to R. So if that be the case, come to the board. Now, if Q is inversely proportional to R, then this means we introduce K. So that Q equals K over R. Now, substituting, I write it in short, then it means that 10 equals to K over a half. Now, I multiply both sides by a half, and I will get that K is equals to 5. So that is the constant, constant of proportion. So if now I put my 5 there where K is, then I'll get that Q equals 5 over R. And that becomes the equation relating Q and R. So those are examples on inverse proportion. And before we go to the third and fourth relationships, now I'm sure we are able to tackle K exercises, KLB, book 3, any addition 3, 4, or 5, you can do exercise 9.2, deals with direct variation, and exercise 9.3 to deal with inverse variation. All right. So we have now dealt with the variations involving two variables, the direct and the inverse. They're just dealing with two variables. In the next part, we look at joint variation. Now, this will involve more than two variables, in either a direct or inverse or both of them combined. Quantities are related by either a multiplication or a division or both of them. All right. So consider a relationship like this one, F equals K mn over R squared, where K is a constant of proportionality. From the previous, we can therefore say F is directly proportional to M. F is directly proportional to N. And F is inversely proportional to R squared. So you can see there are how many variables? 1, 2, 3, 4, but they are all related either in a direct variation or in an inverse variation, and all of them combined. So we look at an example. A quantity VH and R are connected. I should not have said a quantity. Quantities VH and R are connected in the following formula. V equals 22 over 7 R squared H. State the variation between V, R, and VH. First of all, note, we cannot say that V varies directly as 22 over 7 because 22 over 7 is a constant. It's not a variable. So we can't say V varies directly as 22 over 7. But we can say V varies directly as R squared and V varies directly as H. Because that is now what is the relationship between V and R squared, and R and V and H. We look at example 2. A quantity Q varies directly as R and inversely as the square of S. Let's interpret that. A quantity Q varies directly as R and inversely as the square of S. So we say Q varies directly as R and inversely as S squared. So introducing K, we'll have Q equals K R S squared. Now, substitute, I'm writing it in short. We are told that Q is 24, K, when R is 625, and S is 5, so 5 squared. Alright, so 625 divided by 5 squared is the 625 over 25, which gives us 25. So we can say 24 equals to 25K. So what is K? Going there. So what is K? K is 24 over 25. So that becomes the constant of proportionality for that relationship. Therefore, putting K, come back here, putting K on this general equation here, putting K, then we'll have that Q equals to 24 over 25 R over S squared. That is now the equation relating Q, R, and S. We look at this. So this is it. This is what we have said. Yeah. So Q becomes 24 over 25 R over S squared. So what is the value of Q when R is 100 and S is 4? So you substitute now the values in the equation you have come up with, and you get that Q is 6. Alright? So that's an example of joint relationship or variation. We'll continue in the next clip. Alright, so we continue with joint variation, and now we can confidently tackle this exercise on joint variations. So that one, and continued here. I hope it's clear. Alright, so we'll continue with this topic in the next clip.